Hey there, I'm Heather, and today we're going to talk a little bit, just maybe for 15 minutes, about AVO theory and how we use it to discriminate fluids in the subsurface. Okay, so let's start off with what actually AVO is. So AVO is the concept that your amplitudes change with increasing angle or offset. Okay, so think about that bounce point of the reflections in the earth at those interfaces. And so this is a great example that kind of shows a case above where we've got a wet sand, and we could look at the amplitude of that wet sand at 0 degrees, so bouncing that energy straight down and then back up again. And we'll notice that as the angle increases or the offset increases, there's no real change in the amplitude. But if we go down to the gas sand and we increase the angle and the offset, we'll notice now that that amplitude gets much bigger and much brighter. And so kind of in a nutshell, that's what AVO is in a broad scale. And so there's different inputs that we need to perform an AVO analysis. Some of the ones that are really essential are in terms of the well logs, because we need that truthing of the seismic. So the two that are must-haves are having sonic logs and density logs to perform an AVO analysis. It's great if you have other additional well logs to help further truth the analysis. So of course, you know, the more data you have, the better results you'll get, more accurate results you'll have. And even like fluid properties are really essential to have if you can get your hands on them. So things like the API, the GOR, how what's the salinity of your brine. And then temperature and pressure are also inputs into a lot of these too for the full modeling effects. In terms of seismic analysis, we also need either the pre-stack migrated gathers, which are again the best option, or we can also do an AVO analysis with angle stacks. And of course, like with everything else, you want to make sure that that data is as clean as possible. So the gathers are flattened. You don't have any move out still existing in them. And then also that you've essentially tried to get rid of as much noise in the data as possible too. And so AVO kind of goes back to the whole concept of reflectivity. And so I'm just kind of doing a quick reminder here, where we have the energy that comes down. It hits an interface where we have a acoustic impedance contrast between those two rock layers. We've got that reflection coefficient that allows some of the energy to be bounced back and some of it to be transmitted further down. And the big thing I want to point out in this diagram is the angle. And so that's the angle that we're talking about, or if we're thinking about it in terms of being recorded at the Earth's surface, it would be the offset between the source and the receiver, so an increasing in offset. So a 0 angle, a 0 offset would be sending the energy straight down and it bouncing essentially straight back up. So over the years, there's been a lot of work on these AVO equations, and there's a couple of main ones that we tend to go back to time and time again, but this isn't an exhaustive list. So Zopritz has the original equations for AVO. They're very complex, but they do a great job of modeling the effect. And then years later, Aki Richards kind of broke down and rearranged the Zopritz equations into 3 terms, which make a little bit more intuitive sense to geologists. And so he organized them into terms that represent VP, VS, and density. And then Shuey also has a 2-term equation where, again, it's a rearranging of the original Zopritz equations. And it simplifies it into a term that represents the intercept and a term that represents the gradient. And so we're going to start with the intercept gradient concept. What we've got here is the Shuey terms. So we've got A is the intercept, B is the gradient, and then if you have angle stacks that are kind of further enough out, you can actually have a curvature equation, but that's not used very commonly. But when we plot up, as I'm going to show you in the next slide, when we plot up the difference between A and B, looking at how those values align on a chart can give you really good information about what's going on in the pore space in terms of gas, oil, and brine. And so here's an example of what the gradient intercept plot looks like in practice. And so you can see these trend lines. Those are trend lines. It'll look different when you put your real data on them. But what's interesting is that we have our background trend line kind of shown in black. And what we'll see is we'll see this systematic moving away from the background trend if we have oil in the pore space or gas in the pore space. And so that's what makes it, plotting it up this way makes it a really good hydrocarbon indicator. We also didn't talk about AVO in terms of classes, and you've probably heard this a lot too. So the AVO classes, and I'll keep going into this in later slides, are different responses that happen. So right now we tend to talk about 4 main classes. We have class 1, which is where we start off as a peak with our 0 degree or near angles. And then as we increase the angles, the peak gets weaker, so a smaller peak. The example I showed you in the beginning of this mini lecture was having a negative trough that as we increase angle, it gets more negative, so it gets stronger. And so those are a lot of the bright spots that we may be familiar with, like looking in the shallow portions of the Gulf of Mexico. There's also a class 4, which starts off as a trough and then turns into a weaker trough. And then we have class 2. Class 2 is fun because they often start off very weak or around 0, so they don't have a lot of reflectivity at the near angles. And then they become more negative as the angle increases. And one of the things I want to mention here, because I like to use 2p and 2n. So 2p is where you start off positive and get more negative, and 2n is where you start off as a weak negative and then turn into a stronger negative. So, you know, that's just a little bit my thing. Some other people use that terminology too. Okay, so we can look at how all of these look in terms of looking at seismic gathers. So I'll just point out 1 or 2 of these. So here we've got our class 2p. So like I mentioned before, we start off as a very weak positive, a weak peak. And as the angle increases, it crosses over, okay? And then it gets more and more negative. The class 3 I already showed you. So here's class 4, where we start off as a trough, a strong trough that we can easily see. And as we increase in angle, that trough gets weaker. All right. So here's another example. Here we're looking at a class 3. We're looking at it with like the wiggles and the variable density displays, and then an overlay of them. And so our reservoir is right here around 1.55 seconds or so. And what you'll notice in these gathers is we have a very weak, hard to see peak, or trough actually. You know, it actually isn't too much above the noise. And then as we move out with angle and distance, it gets much stronger. And we could see that in any of these 3 displays. All right, so let's go a little bit deeper now. So Rutherford and Williams gave us our first kind of systematic classification of AVO responses, and they had 3 at the time. And so if we look at this table in the middle, they kind of break down the different classes based on the impedance and gradient behavior. Right? I think I got that right. Okay. They focus mainly on gas sands because, as I've mentioned before in a lot of other talks and in the DHI last lecture, that's where AVO effects are the most dramatic. And so some of the things we want to keep in mind is that we can use these techniques, this AVO technique, to help us determine information about not just the fluid effect, but also gleans a little bit of insight into density, velocity, and porosity. Okay, and so one limitation of Rutherford and Williams when they kind of started talking about this in 1989 is that they didn't really consider the thin bed effects or attenuation. So just things to keep in mind. So we could break these down again into each class. Here I'm showing a lot of different visualizations. These were some slides put together by one of my former students. In terms of the different classes, we can see the Poisson ratio, the acoustic impedance, what the synthetics would look like. In terms of amplitudes, the amplitude versus offset, and then kind of that classic chart. And so this is a nice summary slide I like to come back to time and time again, just to think about how all of this information related to the amplitudes can kind of go back to acoustic impedance and Poisson's ratio and so forth. And so let's look at a kind of classic case study from the original papers. So this one is with class 1, and we're looking at the Hartshorn channel sand. And so you'll notice two key features here. First of all, that you can see the polarity changes in adjacent gathers. So we've got two different sets of gathers, so that's, or three different sets of gathers, so that's 3 vertical points, okay? So we've got near to far in one point, near to far in another, near to far in another, and then the increasing angle. And so in this area, if you really focus in, you'll see that these are class 1 sands that show that flip in polarity, and it actually makes them really hard to spot on stack data. So your class 1 sands can actually, you know, with far enough angles, they can flip polarity. Here's a quick example of class 2 from the original Rutherford and Williams paper. And now we're looking at an example from the Brazos River kind of offshore area. So kind of just a little bit south of Houston, Texas, the Galveston area. And so the key characteristic you'll see here, we've got a few areas pointed out right here with green, is, and they're kind of showing them stacked on top of each other more, is that you'll notice that the small angle reflectivity is very close to 0. And so that's one of those defining things with class 2 sands is the at 0 offset or like vertical offset, you don't see much of a signal at all, and rather you see it change as you move out. And so you can notice that gradient, that change in the amplitude, the gradient of change in the amplitude increases as we move out. Here's another case with class 3 sands, which are often the easiest to spot, and probably why we got into that big bright spot mania 50, 60 years ago or so. And so what you'll notice with the class 3 sands is there's a very strong reflection even at the near angles. So you can see that here in these 5 cases. And so you'll see that large reflectivity. You don't see a polarity change at all with these, which makes them even more detectable in seismic. And so that's kind of like why we like them. is they're reliable, they're easy to see, and they often stand out even in somewhat noisy data. Okay, so just as like a quick summary, the class 1 sands, these are ones that are typically found in hard rock onshore environments, and this is a generalization, of course. Class 2 sands can show up both onshore and offshore. So I've seen some of these. They're often in the Gulf of Mexico. They're often below where we have those, they're deeper than we have those class 3 sands. And then class 3 is mainly an offshore phenomena. And I'll just kind of re-mention here that since 1989, we know that there are 4 AVO classes that we really notice. And I believe a while ago there's a theoretical class 5, but I'm not going to talk about that today. Okay, so just kind of a nice summary slide again, just to go over. I'll point a few things out here, kind of adding in that class 4 again, where we start off with a negative trough that gets weaker with increasing offset. So kind of like I'm showing here in the bottom figures. Okay, so kind of wrapping this back into intercept and gradient. I had mentioned before with the intercept gradient plot, we kind of can get that background trend, and then our oil or gas sands will move out away from it. And in different cases, our classes, and you could kind of see it in both of these 2 diagrams, are showing the same thing. So our class 4s tend to plot in this upper left quadrant, second quadrant. And so you can kind of see that by this yellow kind of blob. And then our class 3s plot over here. So they tend to have a negative gradient and a negative intercept. And we could see that when we go back to the reflectivity, the class 3s are this orange color. And so they start off negative. So their intercept is negative and their gradient is negative. So hopefully that helps you see the comparison between these two charts. I'll do that one more time. I'll do that with class 1. So our class 1 starts off with a positive intercept. Okay, it's positive reflectivity, positive intercept, and the gradient gets more negative with time. Okay, so it gets more negative. So class 4 is the only one where our gradient with this yellow line, it's positive, it's moving upwards. And so that's why it plots up here. Oops. All right, we can look at this with some real data. Here's a case where we have the background trend now plotted on there, and then we can see some of the gas sands plotting down here. Typically so we could see those gas sands, and you could see how they kind of break out and away from that background trend. Another way we talk about AVO is in LMR space or Lambda-Mu-Rho space. And so in this case, we're trying to discuss it kind of more in terms of the rock properties, which is great. So lambda is a measure of compressibility, mu is our rigidity, and then rho is our density. And so if we look at those, here we've got our mu density axis and our lambda density axis. And so the different classes will point in different, or will plot in different areas of the Lambda-Mu-Rho space. And one thing that's interesting that I just want to point out here is that we have lines of constant P impedance kind of shown in blue, of S impedance in purple, I think it is. I got that marked wrong. And then, oh no, in red. Going and then or maybe it's and then VPVS in green. I have to, that's not right. The notes are wrong. So ignore that. Those are for different rock types. There's oh, okay, I see what I'm talking about. All right, sorry for that. So these green lines here, we've got too many different green lines on a chart. So these green lines, this lighter green, are the constant VPVS. These red lines that are going across are the constant S impedance. And then these blue lines that are kind of going diagonal are the P impedance. And so I just got too excited by these bigger, thicker lines. So sorry about that. So anyway, that's the Lambda-Mu-Rho space. And so some of the advantages of working with in a Lambda-Mu-Rho analyses is that it can give us more absolute data rather than relative data, but it does require a pre-stack seismic inversion and really careful consideration of what your frequencies and seismic give you. So if you don't have those low frequencies in your inversion, you kind of lose a lot of the benefits of this approach because without low frequencies and inversion, we're dealing more with relative variations. Okay, so let me work on summing it up. So I'm going to show a lot of these key figures again. So we've got all 4 or 5 of these classes with the 2N and 2P. We talked about how the different classes relate in gradient and intercept, and also how this chart, you can kind of see this chart from the classical change in the reflection coefficient first offset, and then what they look like in gathers and where they plot here in Lambda-Mu-Rho space. So all good AVO tools for fluid analyses. And so if you're going about trying to do this, just like some really general advice is you want to start with AVO friendly processing. So you don't want any sort of processing that's been done that degrades or changes artificially your amplitude. You have to have that true amplitude to do these. You got to look at your gathers and your angle stacks. That's kind of one of the first things, it's that same QC, and you've got to have the data available. You'll do some well ties in order to get an idea of, you should always do well ties, but those will help you truth your results at the end, but you need the well logs for the density and velocity information. And so that's hopefully kind of like a general idea of how to get started. And there's some great references out there. SEG has a book all about AVO that Satinder Chopra and John Castagno put out years ago. And that's one I've used when I've taught like a semester class on AVO. And so I'm going to wrap up now with some key concepts. So AVO, if you remember nothing else, it's all about how the reflection amplitude changes with offset or angle. And we relate that to the fluid properties of the rocks. So all of this goes back to depending on the velocity and density and how those change when you have gas or oil in the pore space rather than brine. It's a really great de-risking tool for hydrocarbon prospects. And yeah, and so thanks again for listening to me.